In our previous video, we were working on Lewis dot structures for diatomic molecules. And for that type of molecule, you don't have to give any thought at all to the skeletal arrangement of atoms. You just link the two atoms together. Once you get to triatomic and larger molecules, you'll find that there will be more than one way to link those atoms together. And the more atoms that you have in a molecule, the more possibilities there will be. And I just want to call your attention to the fact that there's only two ways that you can put three atoms together. That would be three in a row or three atoms in a ring. If you have any elements that can form only one bond, such as hydrogen or the halogens, then you can eliminate this cyclic structure because every atom in this cyclic structure has two bonds. Think about the ways that are possible to put atoms together and then start eliminating the possibilities, and this should help you a lot. Let's look at CO2. Let's calculate the number of valence electrons. Oxygen has 6. I have 2 oxygens, so that's 12 from the oxygens. Carbon has 4 electrons, so this gives me a total of 16. I'm going to make carbon the central atom because if you remember back to the bonding patterns that I mentioned earlier, carbon can make 4 bonds. Oxygen typically only makes 2. Carbon has the highest valence. I'm going to put carbon in the middle and attach the oxygens to it. So now I've used 4 electrons to make my 2 bonds. I have to add another 12. So let's go ahead and add the electrons to satisfy the octet rule. I'm starting with 4. I have 6, 8, 10, 12, 14, 16. So I have all of my electrons in here. Each oxygen has 8 electrons in its valence shell. Each oxygen has 3 non-bonding pairs for 6 electrons, plus a shared pair of electrons for a total of 8. Carbon, on the other hand, is short electrons. Carbon is sharing 2 pairs of electrons for a total of 4. I don't have any more electrons to give to carbon, so I'm going to have to move some electrons from the non-bonding pairs and turn them into bonding pairs. So let's push a pair of electrons from each oxygen towards the carbon to form 2 new bonds. And here's my new Lewis dot structure. If you evaluate this structure, you'll see that each oxygen and the carbon now have their octet rule satisfied. As I said, writing Lewis dot structures is a process of trial and error, and making the highest valence atom the central atom is going to work for you most of the time. It's not going to work for you every time. So if it doesn't work out the first time, try something different. Let's look at a molecule that has 4 atoms, and let's think about the possible ways that 4 atoms could be put together. Well, there are 4 ways to do this. All in a line. You could have a branched molecule. You could have a 3-membered ring with a 1-atom branch, or you could have a 4-membered ring. And again, if you have any elements that can only make single bonds, you can eliminate this 4-membered ring altogether. If you have more than one element that can only make single bonds, you can eliminate this arrangement as well. Let's look at this molecule called phosgene, COCl2. And let's first calculate the valence electrons. Carbon has 4, oxygen has 6. I have 2 chlorines for 7 each, for a total of 14 from the chlorines. So my total number of valence electrons is 24. I am going to put the skeleton together with carbon as the central atom. Carbon has the highest valence of all of these atoms, and I'm going to arrange the other atoms around it. In doing this, I've made 3 bonds, so I have used 6 electrons. I have to use another 18. So let's go ahead and distribute our 18 electrons on our terminal atoms. Here I can see that my 2 chlorines and my oxygen all have their octet satisfied, but carbon does not. So this means that carbon is going to have to share another pair of electrons with another one of these atoms. So I'm going to move in a pair of electrons from the oxygen to form a double bond between the carbon and the oxygen. And here's my new structure. If you evaluate this structure and determine the number of electrons in the valence shell of each atom, you will find that all of them have 8 electrons in the valence shell, so they have their octet satisfied. Now you may be wondering how I knew to move this pair of electrons from the oxygen instead of from one of the chlorines. Well, if you think back to the bonding patterns that we talked about, we said that halogens typically form one bond. If I were to move a pair of electrons from the chlorine, that would mean that chlorine would have to have 2 bonds and oxygen would have 1 bond. And those do not fit the normal bonding patterns that I showed you earlier. You will see plenty of examples where oxygen has 1 bond, and in those cases oxygen will have a negative charge. You'll see that when I show you how to calculate formal charge on each atom. You really want to try to arrange the atoms and the electrons in such a way that all of the atoms are neutral, if possible. Let's look at ethene, C2H4. Again, we start every time with determining the number of valence electrons. I have 2 carbons, so my 2 carbons give me 8 electrons. I have 4 hydrogens, so 4 hydrogens gives me another 4. I have a total of 12 electrons in this molecule. I'm going to build the structure, and I'm going to have to attach the carbons to each other. You know this because hydrogen can only make 1 bond, and I can't use hydrogen to link any 2 atoms together. Now I've just started out by distributing my hydrogens evenly between the 2 carbons. In order to put this structure together, I have made 5 bonds, or I've used 10 electrons. I have 2 more electrons that I have to add to this structure. Let's just give them to one of the carbons. If I evaluate this structure, I see that each hydrogen has 2 electrons in its valence shell, and that's good. This carbon on the left has 8 electrons in its valence shell, but the carbon on the right only has 6. So I'll need to use this non-bonding pair of electrons on the carbon, push it in to make a second bond between the 2 carbons. I've made a double bond, and here's my new structure. If you evaluate this structure, you'll see that both carbons have their octet satisfied. Let's look at something that has a positive charge now, H3O+. Calculate the number of valence electrons. 3 hydrogens gives me 3 electrons. 1 oxygen gives me 6. That's a total of 9. But I have a positive charge, so that means I have to subtract an electron. This gives me a real total of 8 electrons. Oxygen has to be the central atom. Oxygen has the highest valence. Hydrogen can only make 1 bond, so hydrogen could not be used to link any atoms together. So I have to make oxygen the central atom and arrange the hydrogens around it. Now I've only used 6 electrons to make these 3 bonds. Let's add in our last pair of electrons for a total of 8. Oxygen has 8 electrons in its valence shell. Each hydrogen has 2. This Lewis dot structure satisfies the octet rule for every atom. However, let me remind you that if we go back and look at these bonding patterns for oxygen, you can see that I told you that oxygen only makes 2 bonds. These are what I'm calling the normal bonding patterns for the neutral atoms. So when oxygen is not charged, it has 2 bonds. In this molecule, oxygen actually carries the positive charge. And you'll see this when I show you how to calculate formal charge. Hopefully, most of this was a review for you, but it's very, very important that you understand how these second row elements come together to make covalent bonds. And we will talk a little bit about third row elements, not too much. We organic chemists are not very adventurous, and we pretty much stick to those second row elements.